Okay, hi everyone. Welcome back to the Novice to Experts Robotics Club. I am Noah. I'm happy to host this first video of the semester, and I will get right into it. So, I hope everyone can see my screen. And I will talk a little bit today about force-sensitive resistors, or FSRs, and how those are relevant to robotics and applications in robotics. So what is an FSR? An FSR, or force-sensitive resistor, is a type of sensor which, when you press down on it, or when a force is exerted upon it, it changes its resistance, kind of like a capacitor, to send a signal. And we measure the resistance across these two terminals here. And in that way, we can measure how much force is being felt by the sensor. So more force equals larger change in resistance. And how it works is you have these two electrodes, which are spaced by this dielectric here across or apart from a conductive film. And when you press down, you change the distance between those two metal components. And that allows you to have an effective change in resistance. And they come in different sizes and shapes here, as you can see, and different applications will need a different shape or a different length of the terminals there. And in terms of robotics, why this might be useful, if you have a robot which is contacting a surface, either in this case you have a wind turbine blade, or if you have a grasping end effector, if you want to pick something up, it may be useful to know how much force that robot is exerting. In cases where you're dealing with a fragile structure, you want to exert not too much force, where you have a limit, you have an upper limit. But also there are cases where you want to exert enough force, so you have a floor there. So some cases you want to exert between those two. So either you have a floor and you have a ceiling, and that's your operational range. And if you have a suite of these sensors attached to the robot, you can keep a good track of what these values are, the forces that the robot is exerting on the surface. So we're going to design a very simple circuit involving this FSR, and I'll walk us through how that would work and what it looks like. So the hardware you would need to start with, you need to have your FSR. That's the core component of this circuit. And you can have any type. I have a square one here, but you could have a circle. You could have a few of them in series, but we'll focus for now on just one. You'll also need an Arduino board. For those of you not familiar with Arduino, that's fine. We're going to take this very simple, basic approach. And maybe later in the semester, someone will focus on how to program an Arduino, and that could be its own lecture. But for now, you have your sensor, you have an Arduino, and then you'll need some basic circuit components, a few resistors, and maybe an LED or two, and some wires to connect that all together. And what the circuit finally looks like is you have an Arduino and you have the FSR connected. Both terminals have to go to, I guess you'd call this the bottom side or maybe the left side of the Arduino. One goes to the positive terminal, the other goes to the negative terminal, and you have a resistor to make sure that you don't short the circuit out in the event of a disconnect. You want to make sure that you have at least some resistance. And on the opposite side, either the top side or the right side, you have an LED to signal how much force you're exerting. So you have a feedback. So the goal is the more you press down on the circuit, the brighter the LED will glow. And there will be some data acquisition later on, but this is more of a visual feedback for the user. And this is a photograph of what the sensor circuit might look like, where you have the sensor on the left, you have your light and a couple of very messy looking wires, and you have the Arduino, which of course is plugged into a computer. And here I can show what the final result looks like, where if you have a couple of laboratory masses, you can put those onto the resistor, and you can see the greater the mass, the brighter the light will light up. And if you put on a very heavy mass, as you'll see in a couple of seconds, it will glow very brightly, and you can use that to qualitatively measure how much force you've been exerting. And it also works for finger taps too, or if you tap, tap, tap on the sensor, you can use this as a way to build a very rudimentary keyboard or a flexible electronic circuit, which might be useful for many applications. That's the hardware, and we've skipped over the coding, which we'll get into right now. The data acquisition is an important component of this, where if you want to determine how much force you've actually exerted on the sensor, this is what you'll need to do. First thing you'll need is to download the Arduino interface, and you can find that at the Arduino website. And you'll also need this packet of software. This is an optional step, but I thought it was very useful, especially for my research. There's this package called CoolTerm, which is developed. It's free to use. It's open source, and you go to this link here by a fellow named Myers, and he developed it. And it's just a way to take the data which Arduino reads from the sensor and convert it into a text file or a CSV file. It exports it in a more friendly manner because Arduino can't do that by itself, as far as I know. But once you have the software downloaded, you'll have to plug the Arduino into your computer, load the appropriate code onto the board, and then you disconnect Arduino from the computer, and then you connect CoolTerm to the board itself. And the software or the website has some steps on how you can do that. But then you connect the CoolTerm to the board, and then you start collecting data. There's a little record button, and you press the record button, and it starts collecting the data from the resistor itself. And it gives you this nice sequential feedback where a lower number corresponds to a very low force, and a higher number corresponds to a higher force. And then you can use different data analysis approaches to determine what your forces are. And this is a very simple code that you need. It's 4 steps, and there are many different ways you could go about this. I found this online at this link down here, but there are different approaches you could take, but generally it will have these 4 steps. You first initialize, whenever you have code, you first initialize what your variables are, and in the case of Arduino, you have to initialize what your pins are, the different locations and what they mean. Once you do that, you have to set up the serial monitor. That's the data acquisition part of the Arduino, and that will give you the readout, as you see on the right there. Then once you've done that, you start what's called the void loop, which is what runs the code. And that will take the sensor and give you a reading. It will print the reading. And that's what this code is showing here, is it gives a number based on what the sensor feels. And then if you have the LED hooked up, this is more of an optional thing, but it's pretty useful for building the circuit without any heavy data acquisition. But you can set up this simple thing which converts, it maps the data from the sensor into a data point for the light. In other words, you're saying, depending on how much force the sensor reads, that's how bright you make the light, and a higher force gives a greater brightness. So that's the code, and there are plenty of sites which give different examples, so feel free to play around with those. But once you have the code set up and you have the hardware, as we saw a couple slides ago, then if you're so inclined, we can get into this data acquisition or the processing of the data. So the raw sensor data might look something like this, where you have small taps, medium taps, and heavy taps. And depending on how quickly you go back and forth and what your delay is, this might look a little bit messy. You might have a much cleaner looking scatter plot, but typically it'll look something like this, where the higher you press down over time, the greater your sensor data will be. But don't be fooled that this y-axis here, this isn't yet measuring in force. This is just measuring in the units read by the sensor. Each sensor might have to be calibrated differently depending on what the physical properties of it are. So what you do for calibrating the sensor is you take some laboratory masses or some known masses, or you can do this with a force machine as well, but you put those on the sensor as we just saw, and then you plot on the x-axis the mass of the weights here. And on the y-axis, you plot the signal response, and it should give you a very nice looking line with a little bit of deviation depending on the masses. But then once you have this, it should be a straight line. And that means that any force that you then find on the y-axis here, say I get a reading of 200, that would correspond to a reading or a mass of about 400. And then you can divide by gravity to get force, if that's what your setup looks like. But it should just be this nice simple relationship of force is equal to some constant times your signal value. And as a quick research note, I've been using this FSR in my research. I have a plate here that I'm wanting to know how much force I'm applying to it if I take a sponge and move it back and forth. And this is relevant for a cleaning robot that I'm developing. But I just have, this is my hand here, and I'm going back and forth with the sponge over the resistor. And you can see the light blinking. The higher force corresponds to a greater brightness. And I have this monitor here, which is reading the data, and it might be kind of hard to see. So I have it on the right here. But it's just the same procedure again, where you have your exported data. You have to feed that into your calibration line, which converts to the appropriate forces or mass. And then I can determine what the equivalent mass is. So in other words, if I scrub down very, very hard, I would be getting readings of around 900 grams or 1,000 grams. Whereas if I do a very light brushing, it's closer to 100 grams. And this is relevant for my research, and I'm sure you can think of different ways of using these FSRs already. As far as applications for robotics and other research practices, these are pretty commonplace in robotics these days, where you need to know how much force the robot is exerting. As a fun example here, we have a little dance floor, or if you've played Dance Dance Revolution, that's another example of a force sensor. It's a little bit beefier or a little bit more robust than the ones I've shown you, but the principle is the same. The harder you press down, you get a different force, and you can change the color based on the force, or you can have maybe a light up like this, so the more brightness would be the force, or a combination of the two. So you can have a very fun dance party that way. And you can even build your very own. If you have a bank of resistors like this, a little grid, and you press down in different locations, it will give you different variables. And you'd have to do a little bit of coding to get this type of result. But the process which I've shown is pretty much the same. You just have to expand upon that. Another instance is if you have these slippers here and you start walking, you can place the resistors in key locations along the shoe or the sole, and you can be able to tell where the person's weight is distributed. So if you need those corrective insoles like the Dr. Scholl's inserts, you can tell, okay, you're putting too much weight on the left or on the insole. You need to put design a custom insole per person, and this might be how you help do that. As far as the more heavy robotics aspect, if you have a robot which has mass handling, if it needs to grab something or touch something, you might need to push hard enough that you crush the can, in this case, whatever it is you're touching. But you need to be careful that if you're handling something more fragile, that you don't exert too much force. And if you have these force sensors hooked up to the robot, this would be very essential in dealing with this sort of thing. And if you have an extreme case of a robot interacting with a person, one of the top concerns for designing a robot in this field is safety. If a robot is very heavy or high inertia and it hits a person, it could hurt the person. We don't want that. So there are robots which are being designed to be less harmful if they contact a person, but we just want to avoid it anyway. So you have a robot which is which has many of these sensors all along its body. And in that way, they act like nerve endings, where you can say, oh, I'm touching this person and I'm feeling that I'm about to hit too hard. I can ease up on how much force I'm applying. So in this way, you can have a person interacting with a robot in a very safe manner. And there are other considerations that need to be made for this, but this is the first step: is how much force am I exerting, and is it too much or is it not enough? So these are a few of the basic steps in designing an FSR system and a circuit involved in that, and a few applications. And I will now open up the floor for any questions or comments we have.
Yeah, I have a question.
Sure.
So I read somewhere about like street tiles that generate electricity. Is that the same concept or something similar?
It's probably very similar. I think if you have, so I'll go back to the diagram here. So if you have a setup like this, where you have two metal plates separated by a dielectric, that's just a capacitor. And you can make these in different forms. So it could be that those sidewalks, if you have two very large plates the size of a sidewalk tile, and when you step on it, you press them together, that changes the capacitance of the system and therefore the effective resistance. So it's the same principle. But I think in that case, there's a little bit more going on, where it's hooked up to some kind of an electric generator. This doesn't generate a current. It just changes the resistance of the panel itself. But you could hook it up in such a way that it does generate current. You would just have to have a little bit more involved with it. But yes, it's the same idea as this diagram here.
Okay, thank you. I also wanted to ask about Arduino boards.
Yeah,
I've heard like online there's like, I don't know, people like look down on people who use this because it kind of like lets you avoid the fundamentals or something. Like
hmm.
engineers say that. Like,
I've heard things like that too, where if you go into the professional or the industrial sector, they don't really use Arduino that much. They prefer to use more hard coding where you need to know either JavaScript or Python. And yeah, I agree that there are definitely shortcuts for using Arduino. But if you have a project you're working on, or if you have research that you're working on, I can't say that anyone would look down on it, but that's probably more based on who your advisor is and what the job is. But that's a good point. Is sometimes you would need to develop a circuit which is much more advanced and doesn't use these boards, but you would use a microcontroller. It would just be a different one like this. And I guess that does bring back to your other point. I don't think any of those sidewalk panels or the more advanced circuits, they don't use Arduino. They use something a little bit more complicated. I don't know what those are, but I imagine it's a bit more sophisticated. But
yeah, yeah.
all this to say, if you're using a project, don't feel bad about using Arduino. I use Arduino. I like it. Sometimes we don't get along, but it's a very useful tool.
Yeah, I was just thinking of like capstone and if I should use Arduino or not, basically.
Yeah, I think if it's for capstone, Arduino is definitely a good tool to have. Maybe I don't know the project, so maybe you would need something else. But if it
Oh
involves,
no. Oh no, it's like far off, but I was just like thinking of it. Like I'm not like I'm not taking it this semester.
gotcha. Yeah, it's when you get there, it would be something to talk about with your advisor in that case. And I'm sure most people will say, yeah, Arduino is perfectly fine.
Okay, thank you.
Sure. Okay, so I'll stop the recording. I'd like to thank everyone for showing up. And of course, this will be posted online. So if you're seeing this online, then thank you again for tuning in.